neutrinos. Right now, this very moment, trillions of them are passing straight through your body. Through your skin, through your organs, through your bones, and even through the entire Earth, as if none of it is there. And you feel nothing. You will never feel anything. Because neutrinos might be the strangest and most elusive particles in the entire universe. Today, we're exploring what neutrinos are, why they matter, and how they've transformed our understanding of physics, astrophysics, and even the origins of the universe itself. Let's begin with the basic idea. A neutrino is a tiny particle with no electric charge. It's unimaginably small and interacts so weakly with matter that most neutrinos pass through everything as though the universe were made of smoke. A neutrino could pass through a wall of solid lead a light year thick and still keep going without hitting anything. Think about that level of ghostliness. A particle that barely acknowledges the existence of matter. So how did scientists even discover these tiny phantoms? The answer starts with a crisis, a genuine physics emergency. In the early 1900s, physicists studying radioactive decay noticed something deeply troubling. In a process called beta decay, an unstable atom emits an electron to become a new element. But the energy release didn't add up. Some of it was simply gone. And in physics, missing energy is not a small problem. It threatens the foundation of the laws of nature. So in 1930, the physicist Wolfgang Pauli proposed a bold idea. Maybe there was a tiny, invisible particle being emitted during beta decay, one so small and so elusive that it escaped detection, carrying energy with it. Pauli apologized for the idea, calling it a desperate remedy. But desperate or not, it was right. This ghost particle eventually got a name, the neutrino, meaning the little neutral one. Finding the neutrino, however, was a completely different challenge. How do you detect something that doesn't interact with anything? For 26 years, neutrinos remained hypothetical phantoms. But in 1956, physicists Clyde Cowan and Frederick Reines finally succeeded. They built an experiment near a nuclear reactor, a place that spews out enormous amounts of neutrinos, and looked for the rare moment when a neutrino actually hits something. And after years of searching, they finally caught one. They directly observed the elusive particle Pauli had predicted decades earlier. Reines later won the Nobel Prize for this achievement. Pauli himself joked that he was glad his little ghost had finally been found. But this was only the beginning. Once neutrinos were confirmed to be real, scientists started investigating them in more detail. They expected them to work one way, but what they discovered threw a massive wrench into physics. You see, the sun constantly produces neutrinos through nuclear fusion. Billions of them pass through Earth every second, so scientists built detectors to measure them. But something was wrong. Humanity was detecting only 1/3 the number of neutrinos predicted. This became known as the solar neutrino problem. Were the detectors broken? Were the calculations wrong? Or was the sun doing something unexpected? Decades of confusion built until physicists made a shocking discovery. Neutrinos, it turns out, come in 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And the neutrinos created in the sun were changing flavors on their journey to Earth. They were morphing, switching identities, transforming themselves mid-flight. This phenomenon is called neutrino oscillation, and it means that neutrinos have mass. Not much, far less than any other particle, but mass nonetheless. This discovery was so revolutionary that it earned the 2015 Nobel Prize. It also meant the Standard Model, the beloved, incredibly successful theory of particle physics, was incomplete. Neutrinos broke the rules. And when something breaks the rules of physics, that's when science gets exciting. But discovering neutrinos' shape-shifting nature raised a new problem. How do you study something that interacts with matter so rarely? The solution: build giant detectors. And I mean giant. Huge tanks filled with ultra-pure water, buried deep underground, caverns illuminated with thousands of photon sensors, detectors the size of buildings. Or in one case, an entire cubic kilometer of Antarctic ice. Super Kamiokande in Japan, one of the most iconic neutrino detectors, holds 50,000 tons of pure water. When a neutrino occasionally interacts with a water molecule, it creates a tiny flash of light. Sensors capture that flash, and scientists turn it into data. IceCube, buried beneath the South Pole, has over 5,000 sensors frozen into the ice. It observes neutrinos from galaxies millions of light years away. In a way, it's a gigantic telescope made not of glass but of frozen Earth. These detectors are some of the most impressive scientific instruments humans have ever built. They allow us to see the invisible. Neutrinos help us answer fundamental questions. First, they reveal what happens inside stars. Light can take hundreds of thousands of years to escape a star's core, but neutrinos zip right out almost instantly. By studying them, we get a live report from the heart of the Sunday. Second, they help us understand supernovas. In 1987, detectors around the world picked up a burst of neutrinos from an exploding star 168,000 light-years away. The neutrinos arrived before the light from the explosion did, providing our first direct glimpse into the inner workings of a dying star. Third, they might solve the greatest cosmic mystery of all, why the universe exists. The Big Bang should have created equal amounts of matter and antimatter. But something broke the tie, allowing matter, the stuff we're made of, to win. Some theories suggest neutrinos might be responsible, tipping the balance in the early universe. These particles might be the reason there's something rather than nothing. Now, let's expand deeper into new territory. Let's explore the parts of neutrino science most people never hear about. Neutrinos from nuclear reactors. Nuclear reactors are among the most powerful sources of neutrinos on Earth. Every fission reaction releases a shower of them. Scientists use reactor neutrinos to study everything from nuclear physics to the safety of power plants. They've even been proposed as a tool for monitoring nuclear reactors from miles away because neutrinos can't be blocked or hidden. In other words, neutrinos could one day become part of global security. Reactors helped confirm neutrino oscillations too. By placing detectors at different distances from a reactor, scientists can literally watch neutrinos change identities as they travel. Imagine observing a particle mid-costume change. That's what these experiments do. Neutrinos from the Big Bang. Right after the universe was born, about 1 second after the Big Bang, neutrinos flooded the cosmos. They've been traveling ever since. This ancient population is called the cosmic neutrino background. It's like the cosmic microwave background, but even older. Someday, detecting these primordial neutrinos will let us see farther back in time than any telescope could ever reach. It would be like detecting a whisper from the moment the universe took its first breath. Neutrinos for imaging the Earth. Here's something wild. Neutrinos could eventually be used to X-ray the entire planet. Because they pass through everything, including the Earth's core, they can carry information about the density of the material they pass through. This idea, still in its early days, is called neutrino tomography. One day, scientists may use neutrinos to map magma chambers, tectonic plates, or even the very center of the Earth. It's the ultimate deep Earth scanner. The sterile neutrino mystery. Scientists now think there might be a fourth neutrino, one that doesn't interact even through the weak nuclear force. This hypothetical particle is called the sterile neutrino. If it exists, it might explain dark matter, the invisible mass that dominates the universe. But sterile neutrinos don't show up in traditional detectors, so scientists look for hints of their existence in oscillation patterns, tiny anomalies that might point to a hidden partner. It's like searching for a ghost by studying the shadows it leaves behind. Neutrino communication. Because neutrinos pass through anything, they might one day become a communication tool. Scientists have already demonstrated a small-scale system that sends a message using beams of neutrinos. It's extremely inefficient now, but imagine sending a signal through the Earth from New York to Tokyo, no cables, no satellites, no interference. The military, scientists, and deep space researchers are all watching this development. The future may be built on ghost particles. The opera speed controversy. In 2011, a neutrino experiment called Opera shocked the world when it reported neutrinos traveling faster than light. Headlines exploded. Physicists panicked. Had Einstein been wrong? Spoiler, no. Months later, scientists discovered the real cause, a loose fiber optic cable. But the episode shows how sensitive neutrino science is. The smallest error can appear to break the universe. The Dune experiment. The next generation of neutrino research is the Dune project in the United States. Scientists will fire a beam of neutrinos from Illinois to South Dakota 800 miles straight through the Earth to study their transformations. This experiment aims to answer the biggest remaining questions in particle physics. Do neutrinos and antineutrinos behave differently? And if so, could that explain why the universe contains matter at all? Dune might redefine physics for decades. We've covered a lot, but it all comes back to one astonishing idea. Neutrinos are everywhere, all the time. They stream from stars, explode from supernovas, flow from nuclear reactions, blow in on cosmic rays, and linger in the background of the universe. They pass through planets, through galaxies, through you. And yet they hold the answers to some of the biggest mysteries in science. They're messengers from the core of stars. They're survivors from the dawn of the universe. They carry secrets about matter, antimatter, and the fate of the cosmos. The more we learn about neutrinos, the more they reshape the story of the universe itself. So the next time you pause for a moment, remember, in the last second, trillions of neutrinos pass through your body. In the next second, trillions more will follow. Silent, invisible, but essential. The story of neutrinos isn't over. If anything, it's only just beginning.